In our first video, we discussed how an optical material is principally defined by its specific refractive index, generally defined as how it influences the path of transmitting light. While this is a crucially important property, it is not the sole characteristic that optical designers consider when choosing the right material for their application. In this segment, we will discuss additional factors that cover the foundation of material properties. Homogeneity. In physics, a homogeneous material has the same properties at every point. It is uniform and without irregularity. Optical materials are also defined by the homogeneity of their composition. Let's consider simple fused silica lens. When installed into a system, this lens is expected to perform consistently across its entire usable aperture, meaning light passing near its center will refract or bend consistently with light passing near the edge. It is the ability of a material to precisely limit localized variations in the refractive index that define the material's homogeneity. Uniform homogeneity therefore allows for tighter control of the transmitting light. Striae. While rarely an issue with today's modern optical materials, striae is defined as distinct lines shaped like thin threads throughout the material. This artifact is caused by incomplete mixing of raw ingredients used in the material's fabrication, producing a final product with poor homogeneity. Most optical materials are considered A-grade or striae-free, with some notable exceptions for certain grades of fused quartz and other low-expansion materials. Fluorescence. Some optical materials, when exposed to high-energy UV radiation, absorb this energy and then re-emit it as light. This process will actually cause an optical material to grow or fluoresce as it releases the absorbed energy. Fluorescence can introduce unwanted noise into an optical system, reducing its sensitivity, clarity, and overall effectiveness. It is therefore important when considering a material to consider if fluorescence is a possibility. Coefficient of thermal expansion. As this term implies, most optical materials both expand and contract with changes in temperature. Since many optical surfaces are polished to a high degree of precision, even small changes in temperature may distort them and adversely affect their performance.
I was in the pool!
Optical designers must therefore account for the environment in which an optic is employed and choose materials which best suit the application. Some materials are classified to withstand the rigors of extreme temperature because of their low expansion properties. For example, precision optics polished here on Earth continue to function properly for years when launched into the extreme cold of deep space. Homogeneity, striae, fluorescence, and coefficient of thermal expansion, combined with refractive index covered in our last video. These are a few of the most important properties to consider when choosing an optical material. Still have questions? That's okay. Our team is always available to assist you in determining which material is right for your application. Head over to escooptics.com to get in touch with us. Be sure to check out our newly released Fast Quote tool. Improving efficiencies and saving you time is just another way our focus is on our customers. Esco Optics, where passion meets precision.